Our speakers for the first talk are Allison Wang and Shujing. They are both software engineers at Databricks, and they are going to speak about polars on Spark.
Yeah, so hello everyone. Thank you all for coming today. My name is Allison, and this is Shujing. So we're super excited to be here and in Bellevue, and I'm very fortunate to see this beautiful fall foliage in Bellevue today. It's sunny, such a sunny day. So today we're going to talk about polars on Spark. So I'm going to give you this evolution of Python UDFs in Spark, and also introduce you a couple of new features in PySpark, and eventually show you how you can leverage them to use polars on Spark. So let's get started. So my name is Allison. I'm a staff engineer at Databricks, and I work on the Spark experience team, which means I got to spend all my time thinking about how to make Spark easier to use, more performant, and easier to debug. So I'm also an Apache Spark committer, and I'm really passionate about the entire Python ecosystem and big data ecosystem. So I will let Shujing introduce herself.
Hi, everyone. My name is Shujing, and I'm also a software engineer at Databricks on the Spark experience team. And I'm super excited to be here today.
Awesome. OK, great. So for today's agenda, so we will start with a quick intro to Spark and PySpark, talk a little bit about the evolution of different Python UDFs, and then we will show you how to run polars on Spark. And we will wrap up with a demo and Q&A. So what is Spark? OK, so Spark is an open source unified analytics engine. It is the de facto standard for distributed large-scale data processing. And it was actually started as a research project in UC Berkeley 12 years ago. And since then, Spark has been widely adopted by many of the major companies you can think of, such as Netflix, Apple, Meta, and most recently, OpenAI, to handle petabytes of data. So Spark also has a massive open source community. It has over 2,000 contributors and 50,000 commits. So here's the chart showing the monthly downloads from PyPy and Maven. So you can see that the download has been increased for more than 7 times over the past 5 years. OK, so the main part of our talk is going to be PySpark. So PySpark is the Python API for Apache Spark. It provides a high-level API and hides all the details about complex distributed systems. So it allows data scientists and engineers to use Python on top of distributed datasets, and they don't need to have a really good understanding on the distributed system itself. And the adoption of PySpark is also massive. There are more than 11 million weekly downloads. But there's something that I really want to highlight over here. As you can see, there's a huge jump in the beginning of this year in terms of the PyPy downloads. And this is a very fascinating new trend. And my personal hypothesis is that it's because of the AI agents. So we're in the year of AI agents. And because Spark has been open source for the past 10 years and been widely adopted by so many companies, I think agents are getting really good at writing Spark code. And I believe AI agents are actually accelerating the PySpark adoption even further on top of the organic growth of PySpark. So if you have any other hypotheses, please let me know, and I would love to hear them after the talk. And it's also super easy to get started with PySpark. So you can use PySpark locally, for example, in Jupyter Notebook. You can just do pip install PySpark, build a Spark session, and you're ready to create any data frames and build your transformations. Or you can try it out in the cloud environment. For example, you can use the Databricks free edition, or you can use Google Colab, which I think you have PySpark pre-built. And I think the version would be PySpark 3.5. So creating a data frame is easy. but the true power of PySpark. And one of the most popular feature is Python user-defined functions, or UDFs. So UDF allows you to run any custom Python function at scale and leverage the full Python ecosystem using any Python libraries or packages that you would like to handle complex transformation logic. And as you can see in the code, it's actually super simple. You just write your normal Python functions and then add the UDF decorator. So this looks incredibly easy and powerful, but what's the catch? The answer is performance. So for as long as the classic UDF has existed, almost every single performance guide has warned against using Python UDFs because they're just so slow. But here we want to go a little bit deeper and understand why it's so slow and what's actually happening under the hood that makes this flexibility of Python UDFs so expensive. Well, there are two main reasons, and we will talk about each of them. The first one is the serialization cost. So Spark runs on the JVM, but UDF code actually runs in the Python process. So there are two separate processes there. And if you want to get data from one process to another one, Spark has to pickle or serialize the input data and send it over to another process. And this serialization and deserialization can be very expensive. So the second one is the execution, the row-by-row execution. So this function will be invoked on every single row. So when you have millions or billions of rows, these overheads quickly adds up, and they can cause significant performance problems for big data workloads. But the good news is Spark community has been long aware of this and has since introduced new types of UDFs to solve these problems. So here I want to talk a little bit more about the evolution of PySpark UDFs. So it all started with the classic UDF, which was actually introduced in 2013. It is slow, but because it's so simple and so easy to use, it's still one of the most widely used PySpark feature today. And then in Spark 2.3, we got the very first major upgrades, the Pandas UDF. It actually addressed both performance problems by using Arrow and by using the vectorized operations. And then start in Spark 3.5, even the classic UDF got an upgrade. It eliminates the pickle serialization overhead. So I actually gave a talk last year, and if you're interested, feel free to check it out. And eventually, in the upcoming Spark 4.1, we're getting this Arrow native Python UDFs, which are very performant and memory efficient. So I know all these concepts can be very confusing, so let's break them down one by one, starting from the Pandas UDF. So I'm sure everyone here is familiar with Pandas. It is the de facto DataFrame library for single-node data science and data exploration. And the PyPy download number here, just massive. It has over 112 million weekly downloads. So this makes Pandas actually one of the most widely used Python package across the entire Python ecosystem. But if you look at the plot, when Pandas UDF were initially introduced in Spark, it's actually still in the very early growth phase. And fast forward to today, Pandas has gone from popular to almost unavoidable. Every single machine learning workflow, notebook tutorials, or even AI agents use Pandas by default. So apart from the advantage of the API, the familiar API, Pandas UDF actually solves two key problems. So first, it leverages Arrow for faster data transfer between the JVM and the Python process. And second, it enables the vectorized operations, meaning that you can actually compute batch by batch to speed things up. So let's take a look at the code. So right here, this is a classic Python UDF. Notice the function signature. It takes in a single Python string and returns a single Python string back. So Spark calls this function one row at a time. And on the right, you see the pandas UDF. So this code is almost identical, except you use pandas UDF decorator. And now this function takes in a pandas series and returns a pandas series. And you can operate on top of the entire pandas series or data frame. So we've been mentioning Arrow a lot. But what exactly is Arrow? So Arrow is an in-memory columnar format. It was actually co-created by Wes McKinney, who is also the creator for pandas. So before Apache Arrow, every system has its own memory format. So every time you move the data between systems or processes, you have to serialize and deserialize the data, which can be very slow and expensive. And Arrow was actually designed to solve this exact problem. So it provides a standard memory format, which enables this fast data transfer between different systems and programming languages. So for example, Spark's JVM and the Python process can now read and write from the same format without any serialization. So this provides a lot of speed up when reading and writing the data. And here is a performance comparison between Python UDF and pandas UDFs. So with Apache Arrow and a vectorized operation, you can see that in this very simple +1 benchmark, the pandas UDF is actually 3 times faster than the classic Python UDFs. But as you might guess, this is still not the end of the story. So what are some pandas UDF's limitations? The core limitation of pandas UDF is that data must be still converted from Arrow batch to pandas series or data frames on the Python side. So there's still this data copy happening. And it adds latency and memory overhead. And also, when you get this large pandas data frame or Arrow batch, when it has to convert this large batch into a pandas in-memory data frame, it can easily lead to the out-of-memory error. And this is one of the biggest pain points for using Python UDFs. And on top of that, pandas itself has some limitations. For example, it is mostly single-threaded, and many operations have pretty high memory usage. So this leads us to the next question. What if we can avoid the pandas conversion entirely? Well, the answer is we can, and that's where the direction Spark is moving. So it's driven by Arrow's massive adoption and maturity. Spark has been adding a lot of new Arrow APIs. So for instance, here we have mapping Arrow, applying Arrow, and in the upcoming Spark 4.1 release, there are 2 new Arrow UDFs. So this is what finally solves our memory and boom issues, and this can give us another major performance speedup. So here is a code example of Arrow UDFs. So on the left, you see this is the familiar pandas UDF. And on the right, this is Arrow UDF. So the only difference here is, first of all, the decorator is Arrow UDF, and you take in an Arrow array instead of a pandas series. So this is much faster because it avoids all the conversion from Arrow to pandas series, and it reduces a lot of memory overhead of building this pandas series and the data frames. So this is it, right? Arrow UDF are our final solution, and it's the fastest possible way. Well, there's one more problem. Well, the native Arrow API, the Arrow UDFs are fast, and they are memory efficient. But they still require you to write logic using the raw PyArrow compute API. So as you can see, this API is not really user-friendly. It's still a pretty low-level API. So for instance, if we look at this task, we want to add 2 columns and times 5. So on the left, this is what we want to write. A simple, beautiful, one-line expression. However, on the right, this is what we actually have to write inside of these Arrow UDFs. You have to use the Arrow compute function, which is, again, it's a pretty low-level API. Well, you can definitely ask AI to write it. But still, it's fine for 1 or 2 steps. But imagine you have a complex feature engineering task, and the code has become harder and harder to read, to review, and to maintain. And eventually, you even want to switch it back to use pandas. So this is our final dilemma. We want the performance of the native Arrow, but we also want an ergonomic, friendly API of a DataFrame. So is there a way to get both? Well, yes, and that brings us to Polars. So Polars is a fast DataFrame library. It was only started in 2020 and already have over 7 million weekly downloads, and it's been rapidly growing. It's written in Rust, and it has this multi-threaded query engine. So all its operations can be pretty parallelized and incredibly fast. And also, it builds natively on this Arrow memory layout. This is actually the key, because it means that when we pass it an Arrow batch from Spark to this Polars UDF, it can actually perform a 0-copy read. So this solves our performance problem and memory problem that exists in Pandas UDFs. And last but not least, it has a beautiful, ergonomic, expressive DataFrame API. So with Polars, we actually can get a readable, high-level code we want in our UDF transformation. And it's actually surprisingly easy to integrate with Polars with Spark using the Arrow API. So in this example, we're using the applying Arrow function to do a normalization step. And the input of the function is an Arrow table. So from there, we can convert this Arrow table to a Polars data frame. And this conversion is 0-copy. There's no serialization, there's no pandas, there's no actual memory cost. So once we're in Polars, we can leverage the Polars API to do whatever transformation we want. And you can see that this API is just beautiful. It's readable, it's easier to understand. And once we're done, we can just call to Arrow and convert this Polars data frame back to an Arrow record batch and send it back to Spark. And that's it. This is the best of the both worlds. We get this ergonomic, high-level API from Polars running on top of Spark's distributed engine with 0-copy Arrow performance. And with that, I will pass it to Shujing for more benchmarks and demos.
Thank you, Allison. Let me start by showing you how we set up the performance and memory comparisons between the pandas-based API and also Polars-based API in Spark. So we ran these benchmarks on TPCDS SF100 dataset, specifically the store styles fact table with approximately 288 million rows. Our task was pretty simple. It just to compute a per store aggregates, including the average discount amount. This is a procedural code in this aggregates functions. And we are running it on 4 worker nodes Spark clusters. Each of them has 61 gigabytes RAM. As you can see in this performance chart, applying the pandas took around 193 seconds, whereas the Polars API just completed in 75.5 seconds. That is around a 2.5x speed up. Why does this much faster? This is because the 0-copy serialization and also the columnar processing. The performance gains are not the only part of the story. Let's also look at the memory usage. This is the distribution of the memory usage consumed by each record batch. The latter, the better. Pandas average around 425 megabytes of the memory usage per batch, whereas Polars use only 275 megabytes. We also wanted to note that Polars has a much tighter distribution with a shorter tail. This means it has more predictable memory consumption and also fewer out-of-memory issues in production. But you might be wondering, that is great for the simple aggregation API, but what do they look like in practice? And how difficult is the migration part from the simple Python UDF to the most efficient API? And let me show you a more practical example of image processing. Here you can see our gallery of 16 sample images with different size of variants. We have the square one and also the rectangular one. Our task is very simple but also practical. We need to find out all images where both width and height exceeds 100 pixels. This mimics a real-world scenarios like finding images suitable for high-resolution displays or filtering out low-quality thumbnails. Let's start with our most familiar Python UDFs. You can just write a simple Python function to do that, to filter images larger than 100 pixels in both images, in both dimensions, and also decorate it with @UDF decorator. It will be a one line of code, and we will get 4 qualified images. The beauty of this approach is the simplicity, but the simplicity comes as a cost, as Allison mentioned. For each row, Spark needs to serialize the data, send it to Python, deserialize it, process it, and send it back. There's a lot of overhead. To address the performance issue, we can now use Pandas API. Spark introduced the vectorized UDFs with Pandas, and instead of processing one row at a time, mapping Pandas processes the entire batch as Pandas data frames. Notice how we are using this vectorized operations of PDF width greater than 100, and which is much faster than a row-by-row processing. We are seeing significant performance improvements here, but Pandas still has relatively high memory overhead, as we saw in our benchmark. Now, let's look at this Arrow-based UDF. The Apache Arrow provides the Colonna memory format that's designed for efficient data transfer between processes. With mapping Arrow, we can work directly with Arrow record batch and eliminating the conversion overhead between Pandas and Arrow. And this performance is much more excellent, and also memory usage is lower. But honestly, if we look at the PyArrow Compute API, it's not the most intuitive. For example, we need to first create this Scala object for these thresholds. And we also need to use their compute function of pc.grader, and we need to manually combine it with mask. It works great, but it's not exactly developer-friendly. So we now introduce the mapping Arrow, but also with Portless. This is where Portless comes in for a more user-friendly API. We get both the performance benefits, but also with a cleaner API. Look how readable it is of this PySpark-like API. Like, we can just simply select the width column and also do the filtering. I also wanted to note in this row, we did a 0 copy read from Arrow record batch. In this case, we maintain both the performance advantages of Arrow while writing code that is as intuitive as Pandas. Finally, if you want to use all this optimization in SQL, Arrow UDTF is your solutions. The Arrow UDTF API lets you take a table in and process it just like Arrow table, but instead of one-one mapping of input and output, the Arrow UDTF allows you to emit multiple rows and columns, just like outputting a table. We can register the function and use it directly in SQL queries. Oops. The declarative table arguments keyword. Let me find my cursor. OK, it's right here. The declarative table keywords lets you pipe in any table, any view, or even a dynamic subquery directly into your UDTF. This can help you turn your function into a powerful, reusable building block in your SQL queries. Yes, I think that's pretty much of my demo. Let me hand it back to Allison.
Thank you, Shujing. This is a very great demo. So we have been talked a lot about pollers and various different types of UDFs. And what are something that we want to do next? So we mentioned a lot of different types of UDFs, but they can be still confusing. So what if we can unify all these different types of UDFs? And as a user, you only need to specify @UDF, and then Spark can actually automatically pick and know what type of UDF it is. So one thing we can do is we can allow user to actually specify the type hints so that the Spark can automatically pick which UDF it is based on the type hints. So this will be a huge win for usability. And next one would be debuggability. So we all know that debugging UDFs can be really hard, especially these UDFs are running in a distributed fashion. So we're working on a new user-friendly profilers for CPU and memory. And also, we want to offer a better way of be able to collect all the log statements inside of UDF so that it will be much, much easier for people to actually debug. And finally, there's one thing that we've all been thinking about. Maybe you can have native polar support, right? What if you don't have to do the from arrow or to arrow? And what if you can just call mapping polars or have native polars UDFs? So all of these are being actively discussed. And our goal is pretty simple: to make Python UDF faster, to make it more memory efficient, and to make it easier to use. Okay, so to wrap everything up, so let's review the key takeaways from today's talk. First of all, if you're still using the classic pickle-based Python UDFs, please avoid using it. Your first choice should always be the native PySpark expressions or Spark SQL UDFs, because they will always be the fastest. But if you must use any custom Python logic, the good option is to use Pandas UDF or the classic UDF with arrow optimizations. So as we mentioned, it is actually much faster because it uses arrows and avoid all the data transfer costs. But it still has this Pandas conversion problem. So the better way is to use the new native Arrow API or the Arrow UDF. This eliminates both the data copy and is extremely fast and memory efficient. And experimentally speaking, the best of the both worlds would be to use polars on top of the Arrow UDFs. You get this zero copy performance and also a clean, high-level DataFrame API. So that's all for today's talk. Thank you so much for coming, and we are happy to take any questions.
Thank you very much for the talk. So we've got time for questions now.
I have a bit of a dumb question because I'm not too familiar with polars, but we do, in some of my work, we built a multi-input, multi-output neural network to do some anomaly detection prediction and things like that. And we built it with, obviously, using the good Pandas UDF. And so I guess with that question, does polars offer something similar as like a MIMO neural network comparable? So I'd love to swap it out and get the speed up. My inference is 4 hours right now, so I'd love to shrink it to an hour.
So polars was primarily designed for the data transformation. Like let's say it helps you to manipulate a data frame. I'm not 100% sure how many machine learning libraries support that it has. But you can definitely check it out using the documentation, I think. So the key part you can think about is, so a lot of operations in Pandas, right? They are very memory intensive, and they're pretty slow. And if you can write part of your logic, maybe not the part that touch the core, like the machine learning functionality, but the other data transformation part using polars, I think that can also help with the reducing the pipeline time.
Yeah. Perfect. Thank you so much.
Thank you.
Any more questions?
Thanks. Firstly, I looked. 4.1 isn't out yet, right? Of Spark. When will it be released? Any ideas? The open source.
Yeah, so it's branch cut has been finished. So I think the 4.1 would be sometimes early next year.
Okay. And then the other question is, if I can do it in polars, I can do it in DuckDB. And DuckDB has better performance. It's a better query engine than polars. So have you done any benchmarks on DuckDB as well?
That's a very great question. Very great question. So everything here you can do with polars. You can also do it with DuckDB. And I personally never done any benchmark between these two, but there are a lot of blog posts online. So where I actually saw one blog post comparing the performance between polars and DuckDB. I think polars from that benchmark, it's slightly faster than DuckDB. But that one include reading data from S3 and performing an aggregation. So I
won't agree with that. But anyway, yeah.
I would love to encourage people to try it out and let us know which one is actually more performant and memory efficient.
Okay.
Thank you.